Alright, so continuing our discussion on quadrilaterals and understanding their properties, in this tutorial we are going to look at the case of a parallelogram and we will try to understand that how do you obtain two congruent triangles from one single parallelogram. Alright, so take a look at this shape. We have a parallelogram P, Q, R and S. Okay, and our objective is to prove this statement that the diagonal in a parallelogram, it divides it into two congruent triangles. Okay, so when you take a look at this parallelogram, it's very easy to see that, well, we have a diagonal PR, right? It connects the two opposite vertices, so it is called a diagonal, right? So as you see here, that this diagonal divides this quadrilateral into two parts. One is triangle PSR and the second is triangle PQR. Now visually you can tell that, well, these two triangles, they look identical, right? But we want to prove it mathematically, precisely that, well, indeed these two triangles are identical to each other or congruent to each other. They are identical in size and in shape. So let us take a look at these two triangles. We have a triangle PQR and then we have another triangle PSNR, right? So this is my triangle number 2 from above and this is my triangle number 1, right? Now, since we want to prove these two triangles are congruent, all we need is one of the criteria. Let's say I'm going to pick on the SSS criteria. If I can get that, it can prove very easily that these two triangles will be congruent. So first take a look at the side PQ. It is going to be equal to the side SR, right? That is the fundamental property of parallelograms. The two opposite sides are going to be parallel and equal to each other, right? And likewise, the side PS will be equal to the side QR, correct? These two sides, right? So these two sides are equal. And then we take a look at the side PR, which is a diagonal and it is common to both triangles, right? So what you have is SSS criteria for these two triangles. And that simply means that these two triangles are congruent, right? That is what we wanted to prove, as simple as that. Nothing complicated at all, right? You don't even need any other properties related to angles or anything for this specific parallelogram. Okay, now I have a homework or a thinking task for you. I used the SSS criteria to prove the congruency of these two triangles, that these are part of this parallelogram. Okay, my question to you is that could we have used ASA criteria or could we have used SAS criteria to prove congruency? I believe we could, but that is something for you to think about, that how would you prove about it, okay? Alright, so with that, now we are going to take a look at a slightly difficult level problem that we are going to be using all the properties of parallelograms or quadrilaterals to solve that problem. Alright, so take a look at this problem. There is a parallelogram ABCD. We know that it's given to us. The angle A is equal to 60 degree. And then there is a line segment AP. It divides the angle A into two equal parts. This angle that we are talking about, right? And likewise, the line segment PB is an angle bisector at angle B, right? So we have to prove three different things. One is that prove that the line segment AD is equal to DP. Okay, that's objective 1. And the second is the line segment PC is equal to BC. All right, so that's objective 2. And the third is, of course, DC is equal to twice of AD. Okay, so these are the three things we have to prove. Okay, so let's start with what is given to us. We have angle A is equal to 60, and we know that based on the properties of a parallelogram, opposite angles are always going to be equal. That means angle A is equal to angle at C, because these are two opposite angles and they both are going to be 60 degree each, correct? And now we can also compute the measure of angle B, because we know that angle A and angle B, they lie on a straight line. And since the line segment CB is parallel to the line segment AD, that means the sum of angle A and angle B is equal to 180 degree, because they both form the supplementary angles, right? We already know what is angle A. That means angle B is equal to 180 minus 60, that will be 120 degree. So now we know that angle B is equal to 120. That means the opposite to angle B will be angle D, and that will also be 120 degree. Okay, so now we have all the four measures of all of these angles in the parallelogram, right? So this is also equal to angle D. Okay, so now let us take a look at this line segment AP. We know that it is an angle bisector, hence angle at vertex A will be divided into two equal parts, 30 degree each, right? Now this gives you a very important result here, that if you look at only the triangle DA and P, we know that the angle D is 120 and the angle at DA and P is equal to 30 degree, correct? Angle D is equal to 120. That means what is going to be the measure of this remaining angle in this triangle only? It's going to be 30 degree, because sum of these three angles has to be 180. 120 plus 30 plus 30 is equal to 180, right? So you simply got this measure, that this is 30 degree. Now, since you have all the measures of this triangle DA and P, we can tell very clearly that the angle DA and P is equal to angle DP and A, and they both are equal to 30 degree, right? And what is a known property of a triangle? We say that when two angles in a triangle are equal, the line segment opposite to those angles will also be equal. That means, very simply, what is the line segment opposite to the angle DA and P? It is the line segment DP, and the line segment opposite to the angle DP and A is equal to AD. So that simply proves that these two line segments are equal. So this is my finding number 1. Okay. By the way, this is what we have proved here, correct? So next, take a look at the triangle PC and B. We know that the measure of angle B is equal to 120 degree, right? It is given to us. We just found it from here, correct? And the line segment PB is an angle bisector. That means the angle at vertex B will be divided into two equal parts. They both will be 60 degree each, right? And also, you know that the angle at vertex C is 60 degree, correct? Because it is directly opposite to the angle at vertex A. We already proved it here, correct? So based on the finding of these two angles of this triangle PC and B, what is going to be the third and the remaining angle? It is going to be 60 degree, because we already have 120 degree covered here. So 180, which is the sum total of all the angles in a triangle, minus 120 is going to be 60 degree. And that simply means that all three angles in this triangle are equal. So angle made at vertex PB and C is equal to angle at B, C and P, which is equal to angle at C, P and B. Okay, and each one of them is equal to 60 degree. Now what does this tell you? That when the angles are equal in a triangle, that means it's an equilateral triangle, right? So all three sides of this triangle are equal, meaning you can state that the line segment PB is equal to line segment BC equal to line segment CP, right? And this is our finding number 2. By the way of this finding number 2, you can say that this is also proven, right? So let me start. What are the things that we have proven here? So we have proven our first two objectives. The only thing that remains to be proven is the objective number 3, okay? So now you can also write the line segment DC as a sum total of the line segment DP, right? Plus the line segment PC. Now line segment DP, we already know that from our finding number 1, it can be equated to AD because they both are equal, right? And the line segment PC, which is this line segment, we know that it is also equal to BC, which is right here from finding number 2. So we can replace that with BC, right? But what is line segment BC? It is the part of a parallelogram that it is exactly equal to the line segment AD, right? So you can rewrite this statement as a sum of two dimensions, which is AD coming from here, right? And BC can be replaced with AD because they both are equal in this parallelogram, right? Or it is equal to twice of AD. And this is our third and the last finding, that the line segment DC is equal to twice of AD. And that's what we wanted to prove in our third objective. So you see that with one slight condition given to you, which was originally that there is an angle A given to you at 60 degree, part of a parallelogram with some conditions that there are angle bisector, we could prove all three things together. It requires the basic fundamental knowledge of the behavior of a parallelogram, that how are angles related to each other. Okay. With that, we will take a pause here and we will conclude our discussion on quadrilaterals, on understanding their properties and so on. With that, I will recommend you guys to go on into our quiz and exam modules to practice a little bit more in strengthening your fundamentals on the properties of quadrilaterals.